WhatBot 2025 is a high-reliability QA task for AI environmental impact. It covers energy usage, efficiency estimation, carbon emissions, and corporate climate impacts. The system must return 3 fields: a short answer, an exact answer value, and precise document references. If evidence is missing, it should refuse rather than hallucinate. Compared with traditional machine learning, RAG stores knowledge non-parametrically in external indexes, so new documents can be added without costly full data fine-tuning. It is also more interpretable because retrieval, evidence selection, and answer generation can be diagnosed separately. The trade-off is higher inference latency, mainly from Elm generation. In this presentation, we focus on our main technical route for WhatBot 2025, a Cohacorig-inspired hierarchical RAG pipeline. It combines hierarchical parsing, multi-query retrieval, re-ranking, context expansion, ensemble voting, and retry. We also briefly discuss hybrid retrieval with ARF, GraphRag, and visual processing as additional directions. AI environmental impact evidence is scattered across papers, reports, and sustainability disclosures. WhatBot 2025 turns this into a strict verification task. Each answer must include a short response, an exact answer value, and precise source references. If evidence is missing, the system should refuse rather than hallucinate. Our main route was inspired by Cohacorig. Flat chunking may lose document structure, single query retrieval may miss evidence, and single pass inference may be unstable. Cohacorig inspired 3 ideas for our pipeline: hierarchical indexing, multi-query retrieval, and ensemble inference with abstention-aware voting. Our main pipeline has 3 phases. First, PDFs are parsed into hierarchical structures and indexed by face and BM25. Second, questions are expanded into 4 query variants, retrieved, re-ranked, and expanded with parent context. Third, multiple Elm runs generate answers, retry handles abstention, and answer priority voting selects the final answer. The first component is hierarchical document parsing. Instead of only using fixed-size chunks, we used PDF typography signals to recover structure. PIMIP extracts font size, bold flags, and text spans. The system builds a section paragraph sentence tree. In practice, sentence-level entries were too sparse, so paragraph-level indexing was used. The second component addresses vocabulary mismatch. A question may use one term, while the document uses another, such as carbon footprint, CO2 equivalent, or GHG emissions. To improve coverage, the Elm generates 3 semantic variants plus the original question. Candidates are then re-ranked by frequency, dense similarity, and BM25 score. The third component is ensemble voting and retry. We use 3 parallel Elm runs to improve answer stability. Blank answers are ignored during voting. More importantly, abstention often indicates a retrieval miss, so the system re-queries the index with a larger retrieval depth instead of using the same incomplete evidence pool. To make the system controllable, we used a strict prompt contract with inline reference IDs and structured JSON output. To make experiments diagnosable, we evaluated for levels, retrieved evidence, final evidence, source citation, and final answer. This helped us identify where each error happened. The first experimental result was surprising. At k=5, none of the individual factors improved the system. Prompt ordering and BG large showed no effect, while multi-query, hierarchical indexing, and retry reduced performance. The real issue was that the candidate pool was too small, so useful evidence was cut off too early. To test this bottleneck, we expanded the retrieval window. In our diagnostic evaluation, hit rate increased from 87.5% to 100%. This confirmed that retrieval coverage was the hidden bottleneck. We also learned that flat chunks offer redundant recall, while hierarchical paragraphs provide cleaner but less redundant evidence. On the generation side, we improved answer accuracy step by step. The base model reached 62.3%. Adding chain of thought reasoning improved it to 74.1%. Enforcing strict JSON output further raised it to 81.5%. Finally, ensemble voting and retry pushed the result to 87.8%, showing that structured prompting and answer stabilization were key to reliable extraction. The final internal evaluation shows that H3 retry achieved the best answer match at 87.8% and the lowest unnecessary abstention at 5.1%. EOK16 full achieved the best Jaccard score of 0.851. More importantly, the error distribution shifted. After retrieval and retry improvements, the main remaining issue was no longer missing evidence, but wrong extraction from already retrieved evidence. This supplementary experiment focused on making evidence retrievable before retrieval even starts. Layout-aware parsing converted messy PDF tables into cleaner Markdown-style tables and text blocks. Regex bounds protected terms like TCO2E, PUE, units, and model names. Finally, scalar and schema normalization reduced string-level mismatch during evaluation. The second supplementary experiment focused on retrieval fusion. BM25 captures exact terms, numbers, units, and abbreviations, while dense retrieval captures semantic similarity. R fuses BM25 top 30 and dense top 30 candidates into final top 10 evidence. This was strong, but it remains an additional experiment, not the main route. We also explored GraphRag as a side route. It helped organize entities, relations, and community summaries, improving interpretability. However, for this numerical and evidence-specific task, it was not selected as the main route. Visual processing was also attempted, but remains future work with Velm captioning and multimodal retrieval. To conclude, our final main route is a Kohakurig-inspired hierarchical RAG pipeline. Controlled ablation showed that retrieval coverage was the first bottleneck. Multi-query and full-ray retrieval retry helped recover missing evidence. The key lesson is to design trustworthy RAG around the real bottleneck, coverage first, then stability and precision.